Started looking at the idea of interpolation. I want to spend today's lecture trying to complete that topic. This will be the second topic within module 4. Regressions was what we had for the quiz. Now this is the other part. Okay. So we did one example with problem 18.6. I'm going to use the same example to illustrate all the four methods we are going to learn. Okay. So the first of them is called linear interpolation. Second of them is called quadratic interpolation. And then the third and fourth, I'll just put their name down. Section Newton's divided difference form method. Divided difference method. This is in section 18.1. And then last method will be section 18.2, Lagrange's method. I'm writing this so that you would understand that any problem can be solved with any method of choice, but obviously one is better than the other, so we want to understand the difference. Okay, Lagrange interpolating polynomials. As far as your exam is concerned, these are the four topics that you have to be good at for the exam. And there are many more methods that are covered in chapter 18. Unfortunately, we don't have time to see them all. So I'll write down the table, which is 1326319, 1326319, 599, 7, 291, 8, 444. So this is a set of data which has 6 values given as 1, 2, 3, 5, 7, 8 and corresponding y equal to f of x values. Okay. So last lecture we went through interpolation and what are we trying to seek here? So now take a pause from writing, look up. We want to find f of 4, which is obviously not on this list, but you do know that 4 will occur between 3 and 5. And you want to do an interpolation between 3 and 5 to get what is f of 4. What else did we see about this data? Is this data linear? Is the slope here for 1 unit change, you get 3 units change. For 1 unit change, you get more than 100 something units in change, or 150 units in change. So firstly, you have to understand this data is non-linear. Okay. 4 happens to lie exactly halfway between 3 and 5. Okay. So we are going to do linear interpolation here, and you will have a slope between for these 2 points. That is, if you plot the values 3, 5, and the corresponding values, which is 19 and 99, you can work out some slope here. What is the slope? 99 minus 19 divided by 5 minus 3. Obviously, that slope will be different between 7 and 8 or between 2 and 3. Okay. So linear interpolation, we did this as, suppose we are interested in 4, we would just say connecting x1, y1 and x2, y2 using a straight line, and let's say this is x naught, this is y naught. We need to solve for y naught, assuming x1, y1 and x2, y2 are or define a straight line. We did this last time, so I'm not going to fully repeat it. So I'll say y naught minus y1 divided by y2 minus y1 equal to x naught minus x1 divided by x2 minus x1, which gives you y naught. Can you, those who were here last time, can you look at your notebook and say what was the value of y naught? especially this is the y naught that we are seeking, which is f of 4. 15? 59. Okay. Y naught was 59 by linear interpolation. So I'll say f of 4 using linear interpolation is 59. Okay. We also introduced a word which we call stencil. The stencil for linear interpolation is, for linear interpolation, the stencil happens to be the 2 points between which you do the interpolation, which in this case, let's say we'll call them x1, y1 and x2, y2, which happens to be for us 3, 19 and 5, 99. By stencil, I mean the 2 points between which you do the interpolation. Okay, and that happens to be 319 and 599. For quadratic interpolation, now this is when you should listen instead of actually writing, because here's a subtle point. For quadratic interpolation, we don't take just 2 points and connect them with a straight line. What we do is take 3 points to define a second order curve, and we want to ask what is f of 4, which is between 3, 5, and what is this before 3? 2. So you can use 2, 3, and 5, which contains the number 4, to have a way of connecting them with the quadratic curve and then figuring out what is y naught equal to f of 4. Okay, so you would write the function y, let's say, is equal to a naught or a plus bx plus cx squared. So I will do f of 2 equal to a plus 2b plus 4c. F of 3 is a plus 3b plus 9c, and f of 5 is a plus 5b plus 25c. Would you agree with me? What am I doing here? Substituting x equals to the known values 2, 3, 5 and the corresponding values of y to get 3 equations and 3 unknowns for a, b and c. You can solve this, can you? Everybody feels good about solving this? Can you solve this? So for get a, b and c. We know what is f of 2, f of 3 and f of 5. So this is basically 3 equations in 3 unknowns. Okay, so we can solve for a, b and c. And this a, b and c is valid for 2 less than or equal to x less than or equal to 5. So if you want f of 4, you would take whatever a is, a plus 4b plus 16c, which is equal to, now you are going to solve this and tell me what is f of 2. F of 2 is 6, f of 3 is 19, f of 5 is 99. You can use your calculator, MATLAB, whatever you want to get a, b and c. Can you? 2 minutes, go. Let's tell me what a, b and c are. Okay. Anyone? Are you solving it manually? You can use your calculator or MATLAB or any software if you can. I mean, this is a problem to test, or this is to understand interpolation, not to understand equation solving. 50. What is 50? No, tell me A, B, and sum.
32, 34, negative 32, and 9.
34 minus 4 times or plus 4 times negative 32 plus 16 times 9 equal to
50.
50. Okay, so we get these values of A, B, and C. Now, did you notice that if you are interested in 4, the number 4, which is between 3 and 5, and I said it's contained between 2, 3, and 5. You might also say that it's also contained between 3, 5, and 7. Right? It's contained also between 3, 5, and 7. So you can also repeat the same procedure with 19 equal to A plus 3B plus 9C. 99 equal to A plus 5B plus 25C. And what is the 7? F of 7 is 291 equal to A plus 7B plus 49C. From this also you can get another F of 4, which is now using 235 as the stencil, and this is 357 as the stencil. F of 4 in this case would be, can you tell? Like you have to again solve for A, B, and C. Now with this set of equations, tell me what is F of 4. And this will be A plus. If you want, I can give different symbols like A dash, B dash, C dash. Harry, are you trying this? Yes, no? We are wasting so much time today. Can you please, all of you, speed up? Are you trying? Come on. Yeah. Do you have a value?
A is 109.
109.
B is negative 72. C is 14.
And this gives you
45.
45. Okay, so the question is then, which is a better approximation? Is it the one with 235 as the stencil, or is it the one with 357 as the stencil? 235 is narrower, 2 to 5 is narrower than 3 to 7. Okay, the estimate using a narrower range is always preferred. Because why is it preferred? Before I write the reason, why is it better to go with a narrower range than with a wider range to do your interpolation?
The numbers we have are closer to the number we're looking for.
We don't know what we are looking for. We know we are looking for f of 4, but we don't know its true value. What we do know is that this data is nonlinear, number one. Number two, if in a nonlinear data set, the wider you make your interval, the more it will deviate from what you think it is. An interpolation polynomial, like saying it is a linear polynomial or a quadratic polynomial, it's basically like saying, even though this original data could be some nonlinear function, I'm going to call it a quadratic function, which gets better the narrower your range is. So you make the range as narrow as possible, because for nonlinear data, a polynomial approximation gets better over a shorter range than for a wider range of x. So in the exam or in your exam, if I give you a table of data and I say get me f of 4 using a quadratic interpolation method, I won't tell you which stencil to pick. I won't tell you pick 2, 3, and 5 or pick 3, 5, and 7. I won't tell you that. But I will expect you to know that it's better to go for a narrower range. Okay. All right. So these two are very simple ideas, like fitting a polynomial, linear or quadratic. Now, if I ask you to do cubic interpolation, like for example, I want you to get f of 4, but using a cubic polynomial as the approximation, what will you do? Which range or stencil to pick? You have f of 4. A cubic looks like what? Cubic is y equal to a plus bx plus cx squared plus dx cubed. And you need to solve for a, b, c, and d. 4 equations, 4 unknowns. If you look at 4, the number, it is contained between 1, 2, 3, 4, 5, and also contained between 2, 3, 5, 7, and also contained between 3, 5, 7, 8. Okay, so you can pick as possible stencils. Possible stencils include 1, 2, 3, 5, and it also includes 2, 3, 5, 7, and it also includes 3, 5, 7, 8. That is 4 is contained in all of these intervals, right? So you could pick this, this or this. The range of this is like 4, 5 minus 1, 4. The range of this is 7 minus 2 equal to 3. I'm sorry, 5. And the range of this is 8 minus 3 equal to 5. I would pick the one with the narrower range, which happens to be this 1, 2, 3, and 5. Solve for A, B, C, and D, and then get f of 4 like this, except we would do f of 4 would be A plus 4B plus 16C plus what is 64D. You can do this, keep on doing this higher order polynomials if necessary. Okay, but the concept is this. Is it making sense? Can't you? You're good? Good. Okay. So now we've covered two methods. Last time we did linear interpolation. So far we have done quadratic, or in general polynomial interpolation. Let's learn a method called Newton's divided difference method, which is described in section 18.1. Okay. Can I erase this part, this one, and this part? Yeah. All right. So suppose you have a data set or data that is plotted like this, something like this. Okay. It starts with, we'll assume x naught, second point is x1, and goes up to xn. So you have y naught, y1, yn. So that is n plus 1 pairs of xi, yi, where I runs from 0, 1, 2 up to n. One thing you should remember is these n plus 1 values are not the entire data set. You might have, let's say, 100,000 data points. These are n plus 1 consecutive values to which we are going to fit a formula. So what I'm trying to say is these n plus 1 pairs are part, or not part, I should say, could be a subset of a larger data set. Suppose you have a data set that starts with, let's say, entry 1, 2, 3, 4 up to, 4. Let's say it goes up to like 10,000. And I might pick a segment which is n plus 1 values, and to which we are going to fit a function. And for any x, that is between x naught and xn, this interpolation is applicable. So suppose these entries are all separated by, let's say they are separated by 10 units. This is 340, 350, up to like 600. Let's say, or maybe that's too many. Let's say that is like up to 370. Up to 390. That is 6 values. Okay. And I'm interested in getting a value 364. F of 364. I'm interested in this. I would take these 6 values, fit a function to that, and use it to compute f of 364. If my interest happens to be f of 420 or 405, so 404, which is not contained here, what I would do is move my stencil to contain the value that I'm looking for. So you would just move the stencil to encompass the value that you are seeking. That is what this whole idea is about. So you start with n plus 1 pairs. Here is Newton's interpolation or divided difference formula. Okay, it's denoted Newton's divided difference formula. This is given as equation 18.7 in the book. And also it's explained in page 495 and page 496. And tape figure 18.5. Okay. These are the kind of formulas you will need to write on your sheet because it's not easy to remember this, right away. All right. Fn of x equal to b naught plus b1 times x minus x naught plus b2 times x minus x naught times x minus x1 plus and so on up to bn times x minus x naught, x minus x1, the product continues up to x minus xn minus 1. This is the formula. This formula is applicable for any x between x naught and xn. What is b naught? B naught is f of x naught. What is b1? Not f of x1. It's written as f of square bracket x1 comma x naught. Okay, this is shorthand for f of x1 minus f of x naught divided by x1 minus x naught. This is a shorthand, like a symbol for the slope. So b naught is like an intercept, b1 is like a slope, and you guessed it, b2 is going to be curvature, which we will write f2 of f of square bracket x2 x1 x naught, which is the difference in slopes. Okay, so this is going to be f of x2 x1 minus f of x1 x naught divided by the extremities x2 minus x naught. which if you substitute this, you're going to get f of x1 or f of x2 minus f of x1 divided by x2 minus x1 minus f of x1 minus f of x0 divided by x1 minus x0, the whole thing divided by x2 minus x0. Obviously, B2 is curvature.
About the B N should replace all the.
We are going to see it next. Next step is to write what is generally Bn. So I put dot 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 here. So you will have a B3, a B4. Suppose n equal to 6, you will have B0, B1, B2, B3, B4, B5, B6. So you'll have to extend this further. So instead of separately writing B3, B4, I'm going to tell you what is Bn. Okay. So this f of x1 comma x0, this is called the first divided difference. F of x2, x1, x0 is called the second divided difference. You can see there will be a third, a fourth, a fifth, and so on. So tell me if you have written this down so I can erase it, and this one and this. If you tell me, I can erase it. So make sure you note this down to where you can find this in the textbook. Okay. All right. So here's the shorthand. So when we write f of xi comma xj, what we are really meaning is this is f of xj minus f of xi divided by xj minus xi. And when we write f of xi, xj, xk, that is, so you don't have to remember the entire formula for this. First thing what you do is you write this as, split it pairwise. F of xi, xj minus f of xj, xk divided by the extremities xk minus xi. Xk minus xi. Then you would split this term using this previous formula, and it goes on. So if I ask you to write what is f of xi, xj, xk, xl, how do you start? How will you start with this? You have a question?
You show that snap, the stencil thingy.
Yeah.
Would you just like imagine if the number goes all the way up to like 10, would you keep doing that for like second divided difference? Like would it be like f x 10 x?
No, second divided difference depends only on three at a time. So if you have x1 or x0 to x10, You can do this only for 3 at a time. You can't do this for all 10 or 11 of them together.
Yeah, okay, so you can only do like 3.
3 at a time. Second divided difference applies only for any 3 at a time. So you can do it between 0, 1, 2 or 6, 7, 8 or like 9, 10, 11, but you can't do it for all 11 of them together.
But and when you, so let's say like you use points like 8, 9, 10, would you use B8 and then B, like for instead of BO, would it be B8?
Yeah. Suppose, that's why I'm just generalizing now it in terms of symbols. This can be 8, 9 and 10.
Okay.
Okay, you would just follow this. Okay. So if you have a divided difference or a this is second divided difference. Yeah. First divided difference. And this is second divided difference. And then this will be third divided difference. And by that logic, this is like the 0th divided difference. So this would be, first you would split it in 3. So this will be these 3 first and then these 3 next. F of xi, xj, xk minus f of xj, xk, xl divided by the extremities xk minus xi. Divided by the extremity, which is XL or XL minus XI. And then you would go about splitting this, and then you would go about splitting this. So it cascades basically. So now we want to write what is the nth order, nth divided difference. So if this is third, what will be the nth divided difference? Remember, 0th involves 1 point, first involves 2 points, second involves 3, third involves 4. So nth divided difference will involve all n plus 1 points, starting from x0, x0, x1, all the way up to xn. Yeah.
So that third divided difference from the x, I, j, k.
Yeah.
You can just find the slope of that, slope equation of that.
So this is slope between I and j. This is the slope between the derivatives of derivatives. It's the difference between the derivatives which makes it curvature. This is like a next level, third order, which is the difference between curvatures, for which we don't have a name.
That would be like this.
Tamagi?
The third difference would be the second derivative since the.
Yeah. Yeah. This is value of the function, intercept. First is this is slope. Second is curvature. And this is like the rate of change of curvature for which we don't have names. And it goes on. So nth divided difference, we will write it as f of xn, xn minus 1, xn minus 2, and so on, x3, x2, x1, x0. I got x1 minus x0. So this must be xi minus xj. Xi minus xj, and this is xi minus xk, and this is xi minus xl. Usually we make this in descending order.
The first one would be f of xi minus f of x of j.
Yes, yes. What I wrote is inconsistent, not necessarily wrong, but it's better to have consistency. So this fn or f of xn minus 1 all the way up to x naught, you would write this as first thing. Take the first n values and then the next n values. So this will be f of xn, xn minus 1 and so on up to x2 and x1 minus f of xn minus 1, xn minus 2 and so on up to x1 and including x naught. And the whole thing divided by the extremities xn minus x naught. So this is the stencil so this is the stencil for the first term and this is the stencil for the second term. So this will be called the nth divided difference. As you can see, this sort of a formula or a formula that is a formula into itself and a formula into itself is best suited for programming. If you write a subroutine that calculates this nth divided difference, after that all you have to do is set n equals 4, 3, 2, 1 and you will recover all the previous values. Okay. So now what we are going to do is to solve the same problem we did before. Compute f of 4. We did with two methods. Now we are going to do with Newton's divided difference formula with n equals 3. Or we'll have 0, 1, 2, 3, which involves 4 terms. So we'll use up to third divided difference, starting with this formula. So once you're done writing, we'll start, okay? Let's keep this formula, okay? We'll keep even this b naught, which is the 0th divided difference, b1 the first divided difference, b2 second divided difference, second divided difference, and to this we'll also add b3, okay? So I'm going to, can I erase this first and second one? Maybe we'll start here. If we are interested in n equals 3, we can choose either 1, 2, 3, 5, or we can choose 2, 3, 5, 7, or we can choose 3, 5, 7, 8. All of them involve 4 points, right? So let's choose 1, 2, 3, 4 because that seems like the so the range between 1 and 5 is 4, range between 2 and 7 is 5, range between 3 and 8 is 5. So we'll select 1, 2, 3, 5. Shorter range, okay? So x naught is 1, x1 is 2, x2 equal to 3, and x3 equal to 5. We are interested in f of x equal to 4. That's what we are trying to compute. Okay. So what is b naught, which is f of x naught? What is f of x naught? 3 from the table. Okay. So this formula here, since we are going to choose n equal to 3, this formula will reduce to b naught plus b1 x minus x naught plus b2 x minus x naught times x minus x1 plus b3 x minus x naught times x minus x1 times x minus x2. Yep, it goes up to n minus 1, which is x2. Is it so clear that it's boring? Okay, everybody agrees b naught is 3. You're good? What is b1? b1 is f of x1 minus f of x naught divided by x1 minus x naught. What is that? 6 minus 3 divided by 2 minus 1, which is equal to 3. We're good? How we got b1 equal to 3? Right? I'm just getting the slope between the first 2 points. And then b2 involves the first 3 points, 1, 2, and 3. X2 is 3, x1 is 2, x0 is 1. You can look at this and say, I recognize this. This is nothing but the slope between 1 and 2. Between 1 and 2. And this is nothing but, this is the slope between x2 and x1. This is the slope between x1 and x0. What is the slope between these 4 points? Between, so this is x1, x0, this is x1, this is x2. What is the slope between x2 and x1? 13 divided by 1, right? 19 minus 6 divided by 3 minus 2. So slope between x2 and x1 is simply 13 units. Or you can do this same thing. That's what I did mentally, but you can also write it. What is the slope between x0 and x1? 3. So this is 3. And x2 is 3 and x1 is x0 is 1. So this is 2. So 13 minus 3 divided by 2 is 5. 10 minus 10 divided by 2. Yeah. So this is 5. Do we all see that this is 5? B2 is 5. It's the difference in slopes divided by the length of the interval. Okay. So then, if you want to get the third, if you want to get B3, to get B3 is f of, my stencil now involves all the 4 points, right? X0 or x3, which is 5, x2, which is 3, and x1, which is 2, and x0, which is 1. This will be f of 5, 3, 2 minus f of 3, 2, 1 divided by 5 minus 1. Take them 3 at a time. Take them 3 at a time, divided by the extremity. And this is, you might remember this directly, or you might write one more step. This is nothing but f of phi 3 minus f of 3 2 divided by phi minus 2 minus f of 3 1 minus f of 2 3 2 minus f of 2 1 divided by 3 minus 1. We already are dividing by a 4. I mean, if I were you, I would not try to memorize all the formulas, but I will try to remember this rule and keep applying it over and over. What is the slope between 5 and 3? 80 divided by 2, 40 units. This is 40 units. Would you agree with me? Yeah. So I'm going to just write the slope and you can agree or disagree with me. Okay. 13, 13, 3. So I have 40 minus 13 is 27 divided by 3, that is 9, minus 10 divided by 2, that is 5 divided by 4. So this is 1. V3 is 1. Would you agree, disagree? Yeah, okay. So we got to put everything in one place. We have V0 equal to 1, V1 equal to 3, V2 equal to 5, and V3 equal to 1. We know that F3 of x equal to B0 plus B1 times x minus x0 times x minus x1 plus B2 times x minus x0, x minus x1, x minus x2. Is that correct? No. Plus B2 times x minus x0 times x minus x1 plus B3 times x minus x0, x minus x1, x minus x2. I'll then put the numbers in 1 plus 3 times x minus 1 plus 5 times x minus 1 times x minus 2 plus x minus 1 times x minus 2 times x minus 3.
So that should be 4. X would be 4.
X will be 4. So this is the function. So not only that you can use it for x equal to 4, you can use it for any number between 1 and 5. So if you wanted 4.2, just plug in x equal to 4.2. So then F3 of x equal to 4 would be 1 plus 3 times 3 plus 5 times 3 times 2 plus 3 times 2 times 1, which is 1, 10, 40, 46. So maybe I'll add a note here. This formula is valid for 1 less than x less than 5. Yeah.
What if you, so it would be different if you did it from like
Like say 2 to 7.
like 3 to 7.
2, 3, 5, 7.
Yeah, would be.
It will be different. You will get different values of these coefficients b, b0, b1, etc. That's the other way of saying if you choose a different stencil, you get a slightly different approximation polynomial.
It would be relatively the same.
My recommendation is you want to pick the one with the narrower range. That is my recommendation. Meaning if you pick 1, 2, 3, and 5, look at the data, the data is highly nonlinear. As x grows in magnitude, y grows drastically. So the slope that you get earlier is very different from the slope you will get later. So you always want to pick a narrower range than a wider range. That's my recommendation. So if you wanted 4, you are better off with 1, 2, 3, 5 than 3, 5, 7, 8 or 2, 3, 5. Yes.
Is BO 3?
Yeah, BO is 3. I mistakenly wrote 1. Which will make this 3. Which will make this 48. Yeah.
Get n equals 3.
Because we are told in the problem, or I'm selecting a problem in which I want to use n equal to 3. We want to do a third order approximation. So if you see this is a linear. So take a moment and see this. If you just call B naught, that is like a constant approximation. If you add one more correction, this makes it B naught plus a linear term. And then this is a quadratic approximation. And then you will have a cubic approximation. Then a fourth order, then a fifth order. So as you add more terms, you add a higher order polynomial to make your corrections even finer. In the limit of large number of terms, you would have almost attained the true value or true function that it becomes nearly exact. But nearly exact means lot of work, lot of computation. That's why we try to see what is the lowest order polynomial which will get you by, so that you have to do less work. So what I urge you to do is that linear and quadratic interpolation are basically special cases of what we saw here. Practice this Newton's divided difference method, and the next method we are going to see. In the exam, these are the only two things I'll be asking. I won't be asking you a question about linear or quadratic directly. I would be asking you to do divided difference formula with n equals 3 or n equals 4 or whatever. Okay, so that was divided difference formula, which again I did one example. I would definitely urge you to do more examples, okay? Just to give you some perspective here. Suppose the data you have follows an exponential pattern, but you don't know. You can write an exponential function as 1 plus ax plus a squared x squared by 2 plus a cube x cubed by 6 plus a to the 4th x to the 4th divided by 24 plus and so on up to infinity. If you just focus on small values of ax, it will look like 1 plus ax is a pretty good approximation. But as ax grows in size, it will look like you need to add a second order correction or a third order correction or a higher order correction. The art of choosing an interpolating polynomial or a degree for the interpolating polynomial is trying to see which order closely matches the data. So suppose you have 3 points which are like this. Okay, if you choose a quadratic polynomial, it will fit the 3. But if you choose a linear, it can only fit 2 of the 3. So the linear is a bad approximation here, whereas the quadratic is the correct way to go. Okay, if you include, say for example, 2 more points, A quadratic polynomial may curve up like this. It may curve up like this, leaving out the last point. So you might have to add a cubic polynomial to include that, or a fourth order to make the curvature as smooth as possible. Okay, so this is really the principle behind it. Okay. There's a lot more one can say, but I have to condense it because I get only so many lectures for each topic, because there are so many topics in this class. I would split this class into 2 classes if I can. So, all right. Everybody has this written down? Okay, can I erase it? Yeah? All right, so same problem, fourth method of the day. Section 18.2, Lagrange interpolating polynomials. Section 18.2. Okay, which is explained in page 502, 503. All right, what is that for polynomial? So for Newton's divided difference formula, we wrote Fn of x equal to B naught plus B1 x minus x naught plus B2 x minus x naught times x minus x1 plus and so on Bn x minus x naught x minus x1 and so on x minus xn minus 1. That was Newton's formula. Lagrange's formula looks like this. Fn of x, Lagrange formula, Fn of x equal to summation I equal to 0 to n Li of x multiplied by f of xi. We are introducing a function called Li of x, which itself is defined as Li of x is equal to product j equal to 0 to n, but j is not equal to I, x minus xj divided by xi minus xj. You know the summation, right? You know what the sigma represents. Are you all aware of what this pi represents, the product? Yes, no? No. So when you write sigma xi, what do you understand? This is basically if I runs from 0 to n, this is shorthand for x naught plus x1 plus x2 plus and so on up to xn. You know this. When I write pi, I equal to 0 to n xi, I am implying the product. This is x naught, x1, x2 multiplied with xn. The symbol pi is used to denote a product, whereas sigma is used to denote a sum. Product of n plus 1 numbers. This is sum of n plus 1 numbers.
That's, what was that symbol right there? That's,
Sigma,
below that.
pi.
Oh, it's fine. And that's just the product, so like,
Yeah. S for sum, P for products.
the product would just be like multiplied times.
Multiply all these numbers together.
So like x 0 times x1.
Yep, yep. Yep. Yeah. Do you have a question? Yeah. So this notation is basically shorthand for j runs from 0 to n. So x minus x naught divided by xi minus x naught multiplied by x minus x naught, x minus x1 divided by xi minus x1 and so on, x minus xn divided by xi minus xn.
That's the product.
Yeah, this is the shorthand of
So we would use the shorthand or we use the longhand?
I mean, when we want to remember things, we use the shorthand, but we know what the shorthand means. So whenever you want, you can expand it. So this is Lagrange's formula, which is actually much simpler and to understand than Newton's formula. If you want a nth order approximation for data or for data points starting with x naught, x1, x2, and so on up to xn. This is n plus 1 data points. All you got to do is remember this summation and then what Li of x means, which is this product. Okay, so now let's solve the same question. Let's get f of 4 using Lagrange's formula with n equal to 3. With n equal to 3. Okay, step 1. That would mean f of n equal to 3 of x equal to, again, it goes without saying that this approximation is valid for x naught less than x less than xn. Same thing as this. So this fn of x where n equal to 3 will first be I equal to 0 to 3 Li of x multiplied by fi of x. Sorry, f of xi. F of xi. That is, there is L0 of x multiplied by f of 0 or f of x naught plus L1 of x multiplied by f of x1 plus L2 of x multiplied by f of x2 plus L3 of x multiplied by f of x3. Before you proceed, you're done writing, pay attention to one fact. This is a function of x. L0 of x or L1 of x, L2 of x, L3 of x, they are all functions of x. Right? Agree with me? It contains x like a variable and x can take any value between x0 and xn. These numbers are particular values of f of x at a certain x0 x1, x2, x3. Right? This is f of x naught. If your x naught is 1, f of x naught is 3. If x1 is 2, f of x1 is 6. These are all particular values. So you can almost think Lagrange's formula works by taking the existing table of data and multiplying them with functions which you can call weighting functions, weightages. Okay, so now it's easy for you to look up these values, right? They just come from the table, come from the data. Shall we now compute this L naught of x, L1 of x, and so on? Okay. All right. Look here. We want L naught of x for I equal to 0. We want L naught of x. What is L naught of x? Here j starts from 0 and goes up to n. In our case, n happens to be 3. So that will include only the first term. It's like going from 0 to 3. Okay, sorry. Yeah, it will be going from 0 to 3. Yeah. So this will be x. Wait, I'm looking for this here. Yeah, it will be x minus x naught divided by I is 3, I is 0. Okay, in this case, I is 0. So I'll have x0 minus, I can't have j equal to I. So the first term will be x minus x1 divided by x1 minus x naught, x minus x2 divided by x2 minus x naught, and x minus x3 divided by x3 minus x naught. No. X naught minus x2, x naught minus x3. Obviously, you are going to get only cubic polynomials because we chose n equals 3. You are always going to get a product of 3 terms, which will make it a cubic. For I equal to 1, what is L1 of x? That will be x minus x naught divided by x1 minus x naught, x minus x2 divided by x1 minus x2, x minus x3 divided by x1 minus x3. Well, it's a little tricky in the beginning, but once you start understanding it, will be easy. We need L0, L1, L2, and L3. So similarly, we'll write for I equal to 2, L2 of x is x minus x naught. Always start with x naught and end with xn, and skip over the value of I. That's it. So this will be x2 minus x naught, and then you will have x minus x1 divided by x2 minus x1 multiplied by x minus, I can't do x2 because 2 and j equal to 2 and I equal to 2 can't exist. So I'll write x minus x3 divided by x2 minus x3. And for I equal to 3, L3 of x is x minus x naught divided by x3 minus x naught. multiplied by x minus x1 divided by x3 minus x1 times x minus x2 divided by x3 minus x2. These are your weighting functions L0, L1, L2 and L3. Is it okay? Now you want to compute f of n equal to 3 and x equal to 4. So wherever x appears, you want to plug in 4, right? So let's do. Actually, what you are going to do is to substitute 4 here. Substitute x equal to 4 here. Substitute x equal to 4 and in L1. Substitute L equal to 4 in L2 and substitute L equal to 4 in L3. So you're going to get this is equal to L naught of 4 multiplied by f of x naught plus L1 of 4 multiplied by f of x1 plus L2 of 4 multiplied by f of x2 plus L3 of 4 multiplied by f of x3. When you say L naught of x or L1 of x, that is a function, but L naught of 4 is a particular value of that function. So there is about a couple of minutes left, I think. So what you could do is compute f of 4 using the Lagrange formula and compare it with what we got for Newton's method. I think for Newton's method, we got 48. F of 4 value we got was 48 for Newton's method. For Lagrange's method, you can compute that and compare. So that's a busy board today. Yeah.
First one, that the xj on the top equals the xi. The very first parentheses, shouldn't it be x minus?
So when you do 0, you skip over x naught. So it should be x naught minus x1.
Yeah.
Thank you. Yep, you're correct. This sort of thing is not conceptually challenging, but without practice in the exam, it can be pretty confusing. So I would, again, it's about practice. So this wraps up our discussion of module 4, which involved regressions, which was covered in the quiz, and then interpolation, which I did partly on the last lecture for about half an hour, and then today one lecture. This is something, this topic, that is interpolation, is something on which I don't have a separate quiz, but when we have exam 2, this is something that definitely will be tested. Okay. So from next lecture, we are going to start module 5, which is numerical differentiation and numerical integration. Okay. So it's an important topic. It sets you up for so many practical applications. So hopefully we'll have a good time. Any questions before we wrap up? No? Okay. Thank you. See you on Thursday.